So this idea was given three numbers. Numbers are abstract entities which are numbing. Basically, they are in a state of numbness. Numbness means when you woke up in the morning, sometimes you feel your legs are senseless. I mean, you have no sensation in your leg, like jiji dhara jetake bole. That is called numbness. Numbness means Bangla ashar. Now here, so these numbers in their abstract sense carry no meaning in them. You give them meaning. Okay. So one meaning we give to a set of three numbers. We construct a 2 cross 2 matrix in this way. Sum over K, linear superposition of all the Pauli matrices, so that X is a traceless Hermitian matrix, because Pauli matrices are Hermitian and traceless. So this is one element, capital X. So any three numbers, any other three numbers you choose, you give it in the same way this meaning, like Y. So another traceless Hermitian matrix. So any number, any set of numbers you can think of as representing one traceless Hermitian matrix. And this set is, not a group, because Hermitian matrices doesn't form a group. This set we shortly denote by, in short, we denote it by the symbol TH2. T for tracelessness, H for Hermitian, 2 for 2 cross 2. Again, to any number you can give a different meaning of a vector, which is basically, its three components are this. So this is one rule. This is another rule of associating different meanings to a set triplet of three numbers, and you get a vector here. For these numbers you get another vector. For these numbers you get another vector. So any three numbers is a vector in this space, and this space is R3, real three-dimensional space. Okay. And we have seen that these objects like X dot Y dot product of any two vectors is equal to 1 by 2 trace of XY. Okay, is equal to XI, YI. And another formula which you proved, that X cross Y dot Z, which is, in terms of these numbers, this is this matrix X1, X2, X3. You all know this is the vector triple product, scalar triple product. This is this number, determinant, this single number. And this number is 1 over 4i in terms of trace of X comma Y commutator into Z. Okay, so these two important relations we have seen. So this basically means this operation with this given meaning of these numbers is equivalent to this operation in this space. Similarly, this operation in this space of matrices is equivalent to this number, this operation in space, in the vector, in the three-dimensional real space, okay, of vectors. So uh, now think of this. You have a space which is TH2. You have a space which is R3. You have three say any for any object here, any vector in the three-dimensional real space, you have corresponding matrix in this matrix space, and they are connected by just three numbers. The components of these numbers are equal, same as coefficients of this number when expressed in terms of Pauli matrices. Okay, so that is a rule which connects these two. These two completely different objects. One is a vector, another is a 2 cross 2 matrix, but they obtain their meaning from a set from triplet of numbers x1, x2, x3, y1, y2, y3, y3. Now suppose, consider, just a minute. Okay, consider a group, SU2 group. SU2, so set of all 2 cross 2 unitary matrices, which is not this. This is stressless Hermitian matrices. This is not SU2 group. This is SU2 group. Say, take any element U in it. So consider a matrix U which belongs to SU2. Now you, just a minute. You take any element from here and take any object, any element in this matrix space. So take X. Now U is a unitary matrix. So its dagger and its determinant are identical. So define this matrix. UX U dagger. So this is, now see, since this matrix, call this matrix X prime, where U belongs to this and X belongs to TH2, set of traceless Hermitian matrices of order 2 cross 2. Now check that X prime dagger is equal to this whole thing dagger. Check this. X prime dagger is this dagger. So U dagger dagger, X dagger, U dagger. Okay, and U dagger dagger is U. So you check X dagger is Hermitian. So you check this is equal to X prime. Clear? So this matrix, which is constructed out of this, is also Hermitian, and obviously 2 cross 2. And you can check trace of X prime is equal to trace of U X U dagger, and trace of this, trace of A into trace of B is trace of B into trace of A. Sorry, trace of A into B is equal to trace of B into A. So it is, this is U dagger into U. Clear? So this is equal to trace of X. U dagger U is 1. Okay, I interchanged these two. And trace of X is 0 because X belongs to traceless Hermitian matrices. Therefore, trace of X prime is 0. Therefore, X prime constructed in this way also belongs to TH2. Clear? Now let's take this three objects, define three new objects like this. Same U, Z different. So you pick up 2 cross 2 one matrix from SU2 group, and with that matrix, for every element with the same matrix, you operate this and obtain a new element of the same group, same set. So all x prime, y prime, z prime, everything belongs to this U, belongs to this TH2. So what U is doing, so think of this space. I have written X, you can do it for any number of matrices. Now, this operation transforms it to another element, say X prime. This operation transforms it to another element, Y prime, and this operation transforms it to Z prime. And this operation is induced by this matrix U. Is done by this matrix U by this rule. It is not U into X, it is UX U dagger. You do this, you get another matrix of this same set. Is it clear? Hello?
Yes, sir. Clear.
Yes, sir.
I think someone is recording.
Yes, sir.
Okay. Now look at this, X prime, Y prime, Z prime. We have done this. Now X prime, Y prime, Z prime being members of this TH2, they have their corresponding members in R3. So members, so vector X, vector Y, vector Z were the members corresponding to a capital X, Y, Z matrices here in this R3. Now similarly, X prime has, since this belongs to TH2 group, X prime can be written as a linear superposition of Pauli matrices, and you take that coefficients of that expansion. That those three numbers, with those three numbers, you think of a vector here. Clear? So that means you take what you are doing, basically you take any U from here, operate on X, Y, Z by this rule U, U, X, U dagger, you get a new set of Hermitian matrices, stressless, corresponding to their corresponding elements in R3 is X prime, Y prime, Z prime. Corresponding element means their components are the three numbers representing their components are the coefficients of this matrix when expanded in terms of Pauli matrices. Clear? So in that sense, you can say that this choice of this matrix U, which directly changes this X to X prime, indirectly induces a transformation in this R3 also, from X to X prime. Clear? Is it clear? So this transformation is basically indirectly induced by this matrix U, which directly operates on this X, Y, Z. I don't know how it will operate on this, because this is a 2 cross 2 is a 3 by 3. So it is a 3 cross 1 column vector. So it is a 2 cross 2 matrix. So it directly operates on this. But by the rule of association between a Hermitian matrix, stressless, and a vector in R3, by that rule, these newly transformed matrices have their corresponding counterpart in R3. Okay, in that sense, this matrix U indirectly induces a transformation in R3. Okay, clear? Now, look at these two relations. Look at this part. That means since vector xyz are same as are equivalent to these matrices, and x prime y prime z prime are equivalent to these matrices. Now let me first write x dot y is equal to, one thing is that because this is the rule of association, xy and x prime dot y prime, the first identity is half trace x prime y prime. This should hold. Clear? ঠিক আছে?
Yes, sir.
Okay.
Now let us check one thing. Let us check trace of x prime y prime. E is equal to, now you know x prime is by definition u x u dagger, y prime is by definition u y u dagger, where u belongs to a SU2 group. Okay, x y x prime y prime all belong to TH2. Okay, now if you see this trace of, in place of x prime you write u x u dagger, in place of y prime you write u y u dagger. Okay, so this is equal to trace of u x y u dagger, because this is 1. This is equal to trace of a into b is equal to trace of b into a. So trace of x y u dagger u, which is equal to trace of x y. Clear?
Yes, sir.
ঠিক আছে? So this means from these two relations, look at these relations. What does this mean? X dot y equal to x prime dot y prime. Clear? That means the transformation which directly induced by u in this TH2 space, which indirectly induces a transformation that keeps the trace invariant, trace of xy invariant. You take any two vectors, any two matrices, product of their trace, calculate it. Now you transform them, the transformed objects, their product of their trace does not change, which equivalently means their corresponding counterpart in the R3, the dot products does not change. Clear? So when a dot product, what kind of transformation in R3 makes dot product does not change? The transformations which does not change the angle between them, x and y. Clear? Now check this trace of the other thing. You see this, you remember this x cross y dot z. This is 1 by 4i trace of x comma y z. Okay, similarly for prime things, I am not writing it, both are same. Now trace of calculate this trace, leave this 4i, trace of commutator x comma y into z prime, because prime things will carry these primes. I am calculating that and you see this trace is commutator ux u dagger x prime y prime into u y u dagger. I'm breaking up this commutator minus u y u dagger u x u dagger into z prime u z u dagger. Clear? So u prime u is 1, this is 1. So you are left with u dagger x y u dagger u y x u dagger. So bring u this side. So this is trace of u xy commutator, there is another u dagger here with this u dagger into u z u dagger, and this is again 1. So this is trace of u x y z into u dagger, and trace of a equal to trace of b, sorry, trace of ab is equal to trace of ba. So consider this as b, this is a, so you interchange, and u dagger will, so you will come this side, u dagger 1. So this is same as trace of x y z. So this also does not change. Okay, that means now consider this space and this space R3 and TH2 XYZ Z prime X prime Y prime. This X prime is UX U dagger, and similarly these others are also related to this. Their corresponding element here are X, Y, Z, and corresponding to elements corresponding to X prime are X prime, Y prime, Z prime. Now, where U is a matrix of, is an element of SU2 group. Okay. Now, what have you seen? Just seen that the transformation induced by U in this space. So you take all matrices in this space, and to that set of matrices you do this transformation. So all these matrices in this set are mapped into another matrix in this set only. So entire set is mapped into itself, but one element is going to the other, so interchanging themselves by this transformation. Now this mapping is associated with, or is corresponds to, another kind of map from in real space from x vector y z to vector x prime, vector y prime, vector z prime, such that x dot y for any two vectors, their untransformed and transformed part has the same dot product, and clear? So now think of the transformation here. You can see that it is induced by this U, but you can't write mathematically in terms of U this transformation, because this is a R3. Every element has 3 components. This is a 2x2 matrix. Now, what kind of transformation in this space can, if you do on any vectors, their interrelations are connected by these equations. One thing is that, so what is this? This is geometrically the volume of the parallelepiped constructed by these vectors, and that volume does not change, and also the angle between any two vectors does not change. Their dot product does not change. So this 2 jointly means that all the transformations which is induced in R3, which has to satisfy these relations, should be rotations in three-dimensional space, because rotations by all the vectors by a given amount in three-dimensional space. By same, if you think of Euler angles, by same in three-dimensional space, by same set of three Euler angles for all these vectors. If you do that, these things will not change, because rotations, all vectors by same rotation in three dimension does not change their dot product, because rotation is not changing their norm and also their angles, respective angles. Rotation is changing the angles of the vector with respect to the coordinate axis, but this is coordinate axis independent thing, x dot y. Similarly, this is this clear? So is this clear that this transformation, which are in this space, forget about this now, in this space, such a kind of transformation which has to satisfy these two relations, that must be a rotation in three dimension. Clear?
Sir, hello.
Yes, sir.
Hello.
Why it has to be rotational period?
Because you take three vectors x, y, z. You take three vectors x, y, z. Draw from origin geometrically. Now do a transformation in them in such a way that this object remains same. So how can you do that? The simplest way is you rotate it without changing, rotate the whole structure as a rigid body without changing the relative angles. You can't, because you have to satisfy this also. So when first one also, so when both you have to satisfy, that means the volume of the parallelepiped constructed by these two you have to satisfy, as well as the angle between any two vectors dot product remains same. That only way it can do is you have to rotate the whole structure about the origin in three dimension in any direction, but there should not be any relative change in angle between any two vectors. And this is the only possible way. So see this geometrically. You rotate this, so this is your axis. With respect to this, everything you rotate like this, so that these take a cuboid, just rotate it in three-dimensional space. So what happens is angle between any two sides, it need not be a cuboid. It may be a, I mean, the angles may not be 90 degree. Take this thing. So one side is x, other is y, other is z. Angles are not 90 degree. Now, if you rotate this in three-dimensional space, all the vectors itself are changing. But what happens? This volume remains same, because you are not changing anything, and also the angles remain same. If you can only want to keep the volume intact without bothering about the angle, then you can do some modifications. You can rotate it and also can adjust the heights accordingly, increase height along one direction, decrease height along other direction. In that way, you can keep the volume intact still by rotating. But then this will not be satisfied. X dot y will not remain for all vectors, all the sides. If you have to satisfy both, you have to keep the norms intact and rotate all the vectors by same amount in three dimension.
Yes, sir.
So that means I picked up a matrix U from this U2 group. SU2 group. I picked up a matrix from this group. And this is the set TH2. There are many elements in it. I operate this U to get this for different elements. Like that, Z also, I am not writing. Z prime like that, W prime like that. Now, this induces a transformation. This transformation, take for one, it changes X to X tilde. Now, just the way I discussed, the change should be such that its norm does not change, and it should be a pure rotation. So, if it is a rotation, then you can say these three numbers, these three components should be related to X, Y, Z by a matrix R, where R belongs to which group? This is a 3 cross 3 matrix. This is a rotation, means norm invariant. So R transpose is 1. Okay. And since it is a rotation, it is a continuous process. Its determinant has also to be 1. So it belongs to an SO3 group. Clear? Sorry. This is X prime. This is X1. This is X2. This is X3. Sorry. Similarly, for this vector, corresponding vector, you will get the Y vector will be related to Y1, Y2, Y3 by the same R, because same rotation skips all the vectors will, because I am taking same U from this only one particular U and doing this transformation. Corresponding transformations are rotations by all vectors will be rotated by the same angle, so that their dot product remains same and cross product, triple cross scalar product remains same. Then this R and this R, because the same U in for X, Y, Z, same R for X, Y, Z vectors. Is it clear?
Sir, why for continuous R determinant should be 1?
Oh, that I said earlier. Because this matrix R, because it is a norm invariant, keeps norm invariant, so rotations. This is 1. So R belongs to O3, set of all 3 cross 3 orthogonal matrices. Okay. Because R transpose is 1 and 3 cross 3. Now rotation. So rotation is a special kind of transformation. This I discussed in two-dimensional space for U1 group, sorry, O1 group, and I don't have these notes here. So by rotation, so think of all matrices R with determinant +1. This corresponds to both determinant +1 and determinant -1. But determinant +1 or determinant R equal to +1, that forms a subgroup. And determinant +1 means, if you write this matrix, if you think of 2 dimension, it is easy. Cos theta sin theta minus sin theta cos theta. Then it has a determinant +1 for 2 dimension. So for R then belongs to O2, and this kind of matrix is the orthogonal matrix, obviously, because you check R transpose is 1 here. Also cos theta minus cos theta sin theta sin theta. This matrix is also a orthogonal matrix, because you check R transpose is 1 here also, but its determinant is -1. Its determinant is +1. Both belongs to orthogonal group, but this is the group element with determinant +1 only. Now, you know, this is the matrix which you get when you geometrically apply use geometry to find how xy will be related to x prime y prime if you rotate by an angle theta, not this matrix. In that sense, you can call this is the only matrix which is rotation, and rotation means there is a vector and you infinitesimally rotate it. So no transformation means theta equal to 0. If you check theta equal to 0, you say this is identity. But this is not identity at theta equal to 0. This is 1 minus 1, 0, 0. So this just operating this matrix corresponding to theta equal to 0 just flips it to the other side. Now this transformation, and if you slowly change theta, here this identity matrix will be slowly, this vector will slowly change its angle. But here it is not that case. From the matrix on which, even if it is a small theta, okay, even if it is theta is small, so this is 1 1 delta theta 1 minus 1 delta theta. So it operates on the vector xy. It will not rotate it infinitesimally. It just changes, because it is 1, it is minus 1, it changes xy to x minus y and then adds delta theta to it, delta x theta, like that. So the vector is completely jumped to another point. So this cannot be achieved by rotation. So only rotation corresponds to this determinant 1 matrix. You check my previous class where I discussed this.
Yes, sir. I get it.
Okay. Therefore, now for getting everything, we can say when there is a group SU2, when there is a group SO3, okay, for every element there is a corresponding element R here. Is it clear? This, we have a way to understand how to connect them. For that, we have to think of a construct. We have to think of this map between these two. But once this map is found, now we can see that at least for every U which induces some transformation here, that induces a corresponding transformation here, that transformation is generated by a SU3 matrix. Clear? Is it clear? বলো কিছু প্রশ্ন থাকলে।
Yes, sir.
Yes,
So,
sir.
then this means when every element corresponding to every element of U, there is a corresponding element of in this group. So one group which is completely structurally different as it seems to start with from this group, but there is a each element corresponding to this, there is an element in this. This is called homomorphism. So SU2 and SO3 are homomorphic to each other. Because we discussed earlier what is homomorphism. Homomorphism So this is an example of homomorphism where one group, SU2 group, a set of 2 cross 2 matrices, there are some rule, however complicated it may be or however simple it may be, to each element I can, so operation of these elements in this space can be realized by, is equivalent to operations of this element in this space. Clear? So every element of U2 is mapped into R3. The way we showed it, we take in U and corresponding to U, we have shown there is at least one element in R which I can associate to U. I have not said, I don't know whether there are more than one elements which is associated to you. We have just, the way we are good, we just find that there is one element in R which is associated with you. So this is a homomorphism. We can't say this is an isomorphism at this point. Clear?
Sir,
Huh.
here we have just checked that the dot products, the inner products are mapped between two sets. So is it sufficient condition for homomorphism?
Yes, it is sufficient condition. Because think of your room. Think of your room, which is a cuboid. Now you cannot change it. You have to alter the shape of the room. Your condition is you can't change the volume of the room. So if that is the only condition, you can bend your rooms, three sides of your adjacent sides of your room at different angles, and increase their length in order to keep that volume unchanged. But on top of that, the volume is unchanged. On top of that, if you need the condition that x dot y should be remain same, then you can't do this. You can't alter the angle between the rooms and the length simultaneously. That is a sufficient condition.
Yes, okay.
Okay. So always try to think in terms of geometry. তো এটা বোঝা গেল? It is so for one element in this, এটা বোঝার জন্য আমাকে U is a transformation on which it will operate. R is a transformation on which space it will operate. How these two spaces are connected on which the transformation is operational, that we have to first decide to determine to find out whether there is a, if we can find a relation, then we can say we have obtained a homomorphism between these two groups. Clear? Then I